Okay, so welcome back. What did I do last time? Oh yeah, that's right. I have it here on the camera. So the thing we ended with was the spanning set theorem, which is kind of sort of the thing that ties together the importance of our definition of basis. It's the thing that basically tells you why. Basically, I didn't mean to say that. So it's the thing that basically tells you that the basis is you know the idea of the most efficient spanning set for some given subspace. So just remembering what this says, if you have a set of vectors in vector space V, and let H be the subspace that's generated by that set of vectors, or subspace spanned by that set of vectors, then if one of the vectors in this set of vectors, so S is a set of vectors, S is not the span of these vectors itself, that's H, right? So S is literally just a list of those P vectors. Okay, so if one of the vectors in S, we'll say it's V sub k, is a linear combination of the remaining vectors in S, then if I consider the set formed from S by removing that V sub k, that set still spans H. So the space spanned by that list of vectors still spans the exact same space if I remove a vector that's a linear combination of the others. And so what this is saying is that when you have a linear dependence relation among the vectors, when you have a vector that is, or that can be written as a linear combination of the remaining vectors, that vector is adding nothing to the span. It's essentially redundant info. And I mean, that is literally what's going on. If you think about what a linear dependence relation is, algebraically, it's saying that you could have formed that vector from this span operation with the other vectors anyway. So throwing that vector in the mix doesn't add anything, right? It doesn't give you more that you are spanning because you could already make up that vector from the other vectors. So you're literally adding in redundant info there. And so removing that piece of redundant info does nothing. It doesn't alter what's going on here. Okay. All right. The second bit is that if the subspace spanned is not the zero subspace, then some subset of S is a basis for H. And so what this is saying is that if you repeat this process in one, so one, technically wields a pretty or yields a pretty crude process here, where you could just look at your list of vectors, determine is one of them is that list of vectors. So I have H, which is my subset spanned by these vectors. I can look at that list and I can ask myself, is that list linearly independent? Okay. If it is, then I already have a basis for H. Okay. If it's not, then by our previous theorem, which I don't have for underneath the camera, maybe I can refer you to that theorem. It's theorem 4 in the textbook. It's in 4.3. It's the first boxed theorem. So this theorem says that if we have a set of vectors that's linearly dependent, then at least one of those vectors can be written as a linear combination of the others, right? And so if you have a set of that is not linearly independent, then at least one of those can be written as a linear combination of the others. Okay, so then by one, I toss that one out, and I still have a spanning set for H. I ask the question again, is that set linearly independent? If it is, then I now have a basis, and of course, my new set is just S minus that one vector. Right? It's just S where I've removed that one vector, so it's definitely a subset of S. Okay, and if it's not linearly independent, then it's still not a basis, but by this number one fact here, I can remove the vector I'm guaranteed is a linear combination of the others, and I can repeat this process, right, all the way down. Eventually, I will toss out all those redundant vectors, and what I'll be left with is a set that spans H that is linearly independent, and so by definition it's a basis. Okay, so that's the idea here. Okay, so what is our main application of this, or our first direct application of this? It's finding bases for the null space and the column space. So what about finding a basis for null A and the column space of A? Okay. All right. So let's consider maybe for our first example. Let's find find a basis for the column space of B, where B is the matrix B1 through B5, and this matrix is equal to reading column-wise 1 0 0 0 4 0 0 0 0 1 0 0 2 minus 1 0 0 and 0 0 1 0. Okay. All right. So, how do I find a basis for this? What is the column space of B? So note the column space of B is, I'm not going to rewrite all these, that would take too long. I'm going to write this as the span of all the vectors, all the column vectors, right? So it's the span of the set of vectors, which is all the columns of B. Okay. Now, this is clearly not going to be a basis for the column space. Why? Well, these 5 vectors are not linearly independent, and they're not linearly independent just by looking at them, right? So you notice that B2, for instance, is 4 times B1, right? And you can clearly see, because this is a very easy matrix, you can clearly see that B4 as well is a linear combination of B1 and B3. Right, it's 2 times B1 minus B3, or 2 times B1 plus minus 1 times B3. Okay, and so you can immediately see that you have 2 vectors here that that could be tossed. Okay, so note we can delete B2 and B4 from this set to still get a spanning set. Okay. Why B2 and B4? Again, B2 is a linear combination of B1 and then 0 plus the rest. It's 4 times B1, right? So B2 is 4 times B1. And B4 is 2 times B1 minus B3. Okay. All right. Now, we were lucky here that this matrix was simple enough that we could actually see it. Had enough zeros, and the vectors in question were simple enough that we could actually see what was going on here. In general, right, this process might be a little trickier. Okay. So, and we'll see exactly what it is that goes on in that case. All right, and so we're looking here. We can delete B2 and B4 from this set to still get a spanning set. What does that mean for us? So continuing on this example. Okay, so that means that the column space of B is actually spanned by B1, B3, B1, B3, and B5. Okay. But let's look at B1, B3, and B5. Okay. So here's B1, here's B3, and here's B5. Are those linearly independent? Well, yes, they are, right? These are linearly independent. And so after discarding those, I get a set that is linearly independent. How can I say that that set of vectors is linearly independent? Well, because of how the entries in those vectors work, I can clearly see that no vector in that set is a scalar multiple, or is a linear combination of those that precede it. So that's it. So what is this? This is the span of 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0. Okay. And these three vectors, so B1, B3, and B5, are linearly independent. Again, to see that, you could just say, look at these vectors. None of them is a linear combination of the other two. So you're good to go. These are simple enough that you could use some basic reasoning like that. Right. So the point is that you're deleting the columns that don't have the pivots in them, right? You're deleting the columns that don't have the pivots because what is meant by that? If they don't have the pivots, looking here, if they don't have the pivots, then they can be formed from the columns that do, is the idea here. Okay. They can be formed as linear combinations of the columns that do. Right. Okay. All right. So in that case, the B that we were given was extremely nice, right? It was some very, very simple matrix here. Okay. Now let's consider a second example. Suppose that A is a matrix made up 5 columns. So its fifth column is A5 here. And when I write out this matrix, so I'm going to write out this matrix column-wise again. So this is 1, 3, 2, 5, 4, 12, 8, 20, 0, 1, 1, 2, 2, 5, 3, 8, and then minus 1, 5, 2, 8. Okay. All right. Now, suppose I know that A is row equivalent to the B from before. Okay, I still want to find a basis for the column space of A. Okay. Okay, so how do I do this? Well, let's remind ourselves that here was B, and B had 3 columns that ended up being the only ones we needed to span the column space of B, and those were linearly independent. Okay, and we know that A is row equivalent to B. Okay. Now, we saw before that in B, for instance, the second column of B was 4 times the first column, and the fourth column of B was 2 times the first minus the second column, or sorry, minus the third column. So I wonder if that relationship is actually true for A as well. So note, so from before here, if we label these B1 through B5, and these are A1 through A5, I have that B2 is equal to 4 times B1, and B sub 4 is 2 times B sub 1 minus B sub 3. Okay, so that's the two linear dependence relations that I get for this matrix B. Okay. Now, A is row equivalent to B, but of course the matrix A is different from B. So here's A, here's B, the matrix it's row equivalent to. I wonder if the same linear dependence relations in the columns of B apply to A. Well, we can just check. Right, you can check that this is the case. Note that the second column of A is 4 times the first column of A. Neat, right? 4, 3 times 4 is 12, 2 times 4 is 8, 5 times 4 is 20. And what about the fourth column? So what is A sub 4 here? Is it 2 times 1 minus minus 0, that's 2, okay. Is this 2 times 3 minus 1, that's 6 minus 1, that's 5, yep. 4 minus 1 is 3, yep. 10 minus 2 is 8, yep. So it's 2b1 not 2b1, 2a1 minus a3. So what does this tell me? Well, I have the same linear dependence relations between the matrix B and the matrix A. Okay, that's the same linear dependence relations between the columns of each, I should say. I should be careful there, right? I'm not mixing the A's and B's here. So the point is that whatever linear dependence relations exist between the columns of B will also exist between the columns of A and vice versa. And so that is going to be true for row equivalent matrices. Okay. And so, because if I end up having a linear dependence relation among the A's, that is going to result in a linear dependence relation among the B's and vice versa. And so what this tells me, first of all, so this tells me two things. So this tells me, one, I can toss A2 and A4, and two, the remaining columns are linearly independent. Now, why does it tell me that? Well, so these facts, regardless of where I got them from, these facts tell me I can toss A2 and A4 because I have linear dependence relations, okay, between them and other columns. So, so this thing that I've boxed tells me why I can toss those two vectors, so I can throw those out. The remaining columns are linearly independent. The reason for that is that if they weren't, if there was a linear dependence relation among the remaining three columns, that would imply a linear dependence relation among the three columns of B that were left over, but there's not one, right? There's not one. And so that is the reason why what's left is linearly independent. And so what is a basis for the column space of A? So col A can be written as the span of A1, A3, and A5. Okay. So here's A1, here's A3, here's A5. So the set A1, that is the vector 1, 3, 2, 5, A3, which is the vector 0, 1, 1, 2, and A5 is a basis. So this is a basis for the column space of A. Oh, there we go. Yes, B is the reduced row echelon form of A, right? Okay, so yes, this is going to lead us to the general way of doing this. All right, and so what is the idea here then? So I have a generic matrix A. I row reduce it. If I want to find a basis for the column space of A, I row reduce it to get its reduced row echelon form. Here's B. All right. In B, what columns am I looking for? I'm looking for the pivot columns. And it's the pivot columns that I find, right? So these pivot columns are easily identifiable in its reduced row echelon form. The pivot columns, not as they show up in the reduced row echelon form, but as they show up in A, form my basis. This is the very important fact. Okay, note, right? Note the columns of, so the pivot columns of A form the basis for the column space of A, not the pivot columns of B. I.e., in that example, the basis for A is 1, 3, 2, 5, 0, 1, 1, 2, and minus 1, 5, 2, 8. So this is my basis for the column space of A. Okay. But this is not. Can anyone tell me why in the chat you can tell, right, that this is the correct basis and this one cannot possibly be? Right? Remember what the column space is. The column space is the set of linear combinations, right, of the columns of A. Right? Here's the columns of A. Here's what they look like. Okay. All right. But what do you notice about the vectors in this set that you could never get? And so think about that for a second. Yeah, right. So A has stuff in the last row, B doesn't. So what that means is that if I'm forming linear combinations from this set, no matter how hard I try, what's the last entry? It's 0. Last entry is always 0, right? But look, the vector 1, 3, 2, 5 is clearly in the column space for A because it's the first column of A, right? But the vector 1, 3, 2, 5 could not possibly be formed from any linear combination of these three vectors because they only have zeros in the last entry, right? And that's exactly right. So someone said linear combinations for the columns of A are not the same as linear combinations for the columns of B. So even though you have row equivalent matrices, you can't just pick the vectors themselves, right? So it matters, okay? And so this bears repeating one more time, the following fact. So I'm just going to repeat this again for emphasis. The pivot columns of a matrix A form a basis for the column space of A. And so what is very, very important is that now we have a process for finding this, right? So our process for finding this is we take A, we row reduce it, right? We put it in reduced row echelon form. We identify the pivot columns in that reduced row echelon form, but then we go back to our original matrix A, right? We go back to our original matrix A and say, yeah, right, it's the columns of A that make up the basis for the column space. Okay, so it's the basis, it's It's the columns of A that get the job done, not you. That's where you need your basis to come from. Okay. Okay, so any other questions about that? This is you definitely have to know this. This is an extremely important fact. And like I said, the warning is it's such a bad mistake if you write down the columns of the reduced matrix as as forming a basis for the column space, even though it's easy to do. It's a bad mistake enough that you will get docked many points for such a problem if you were asked to do that on an exam. Okay, now I still have a question. How do I find a basis for the null space of A? Actually, this is something that's really nice. So our process earlier of explicitly describing a spanning set for null A automatically is a basis. All right. Now, I'm not saying that if you find any spanning set of null A, it's a basis. That's clearly wrong. But if you found your spanning set of null A through that process that we used earlier, then the result is always a basis. So the resulting list of vectors always forms a basis. Okay. All right, so that's the last important bit about that. Okay. So, what is the next step? This next section is typically skipped until later in the chapter, but I'm just going to go ahead and do it now. So I want to talk about coordinate systems. And now that I have the notion of a basis, the idea behind coordinate systems is made a lot clearer. In fact, I can actually define these things now once I have a basis. So one way that you can think about the benefit of a basis, and this is really kind of the most important place where using a vector space, generally like an abstract vector space, has benefits over just using Rn. It's when you want to do things like express a single quantity using two different sets of coordinates, using something called a change of basis. Okay, it can turn out that one basis is, more convenient to work in than another. So I'm touching on something that I might not have mentioned except just in passing before, but there's a quick question, which is, are bases unique? Right? That is, if I have either a vector space or a vector subspace, and I have a basis for it, is that unique? Is it the only basis? Well, you should quickly figure out the answer to that is no. It's clearly not unique. If you have one basis, you could easily get another basis, quickly by just doing some type of nice, operation on one of those vectors, right? You could scale one of those vectors, for instance. So that clearly changes the basis. Technically the list of vectors changes, but of course it doesn't change the span. It doesn't change the substance behind it. But a basis is technically not unique for that reason. But sometimes one basis might be more convenient to work in than another. And so the idea is that bases give us a way of putting coordinates on a space, for us a vector space. And so what do I want to say here? The very first thing I want is kind of the thing that enables everything that follows. So this is the unique representation theorem. So bases are not unique, but there's a unique way of expressing, say, a vector relative to some basis. Okay, so let script B, which is a set of vectors b sub 1 through b sub n, be a basis for a vector space V. Then for each x in V, there exists a unique set of scalars the fact that they're unique is important here. So there exists a unique set of scalars C1 through Cn such that x is C1, C1 B1 plus C2 B2 and so on all the way up to Cn Bn. Okay. So the proof's pretty easy. We know that B is a basis, so it spans V. That's why we can write it as a linear combination. The fact that these are linearly independent tells me that I have the uniqueness here, right? If I think about this as a vector equation. Okay. All right. So what is the purpose of this? This allows me to define B coordinates. So this allows me to define coordinates relative to a basis. Okay. So what is that going to be? So quick definition here. Let B be a basis. So let this be a basis for a vector space V. Let X be in V. Okay, the coordinates of X relative to the basis B or the B coordinates so the B coordinates of X, we'll say, are the weights C1 through Cn. It's that unique set of scalars you get by the unique representation theorem. Okay. Such that, that pin's no good. So such that X is equal to C1 B1 and so on, all the way up to Cn Bn. Okay. All right. Okay. So we write this as the B coordinates of X. So it's bracket around X with the subscript B. And if X can be expressed as this linear combination, its B coordinates are simply the vector where the entries are those weights, C sub I. Okay, so this is called the coordinate vector of X relative to B. Okay, or the B coordinate vector of X. I'm going to use these interchangeably. Also, the map, and this is important, that sends a vector X to its B coordinate vector is called the coordinate mapping. So this is the coordinate mapping determined by B. Okay, so that's a lot of terminology here. What do I actually mean by this? So very, very easy example here is the following, right? So this might seem kind of fancy at first, but note this, you've very much been doing this for a long time, right? The first time you ever labeled a point like an ordered pair in the plane, right? You've been doing this. So how does this work? Well, here's an example. Note, let's say that I have the vector x, and I've written that vector. So I'm looking in Rn now, right? And in Rn, I write a vector x as 1, -3, 5. Right? What do I mean when I write a vector as 1, -3, 5? Well, one way of viewing this is that this is 1 times the standard basis vector E1, -3 times the standard basis vector E2, plus 5 times the standard basis vector E3. Right? So I have weights describing a linear combination of x expressed in terms of linear combination of standard basis vectors E1, E2, E3. And so if I look at the set B, that is my standard basis vectors, E1, E2, E3, then what could this be called? These are the B coordinates, right? So if I slap the B coordinate symbol on X here, the B coordinates of X, where B is the standard basis vector, are the normal coordinates you've been using all your life, right? So this is exactly the same thing you've been doing. It's just that in Rn, you're always doing it with respect to the same basis, right? So up until now, you've always been labeling the coordinates in Rn by, referring to the same basis, which is why it's called the standard basis, right? But you can use any other basis of Rn you want, right? So you could use any other basis of R3 that you liked here. So let's do another example. Here's another example. So let B be a set of vectors B1, B2, where B1 is the vector 1, 0, and B2 is the vector 1, 2. Okay, this is a basis for R2. So then B is a basis for R2. So B is a basis for R2. Suppose X in R2 has the B coordinate vector. So that's X sub B here. Let's say that that is -2, 3. Okay, find X. Now, there's a reason why I did my very first example involving the standard basis of Rn, because as it turns out, what we're doing now with coordinates is actually a special case of something done via what's called change of basis or change of coordinates, which we won't do until a little bit later in the chapter, which is why a lot of times this section is skipped until later, but I'm just going to go ahead and do it now. Find X, and what I mean by find X relative to the standard basis of R2 is really what's going on. Okay, so then how do I do this? Well, note X, its B coordinates being -2, 3 tells me that whatever X is, it's -2 times B1 right, plus 3 times b2. That's what it is by definition. That's how these coordinate vectors are defined. And so I can just compute this, right? This is minus 2 times 1, 0 plus 3 times 1, 2. And so this is minus 2, 0 plus 3, 6. And so this is the vector 1, 6. Right? So the vector x with respect to the standard basis is the vector 1, 6, but with respect to this basis b, it's the vector minus 2, 3. Okay? All right. All right. So another definition. I think it's like script E. What's my best way of writing script E? I don't want to put the curly Q thing in there. That makes it look like it's almost like a zeta or something. We'll write it like this. So this, we'll call this script E. This is the standard basis of Rn. This is the standard basis of Rn. Okay, and so another way of viewing this 1, 6 is that, well, this is with respect to the standard basis, right? So technically, if I wanted to, I could basically replace all these scribblings, all these writings of anytime I have a vector is equal to some specific thing, I could put this stupid bracket notation around it. Of course, that would add a bunch of time. There's no reason to do that when there exists a standard basis that's nice like this. Okay, and so what is a way of viewing this maybe intuitively? What is it that's going on here? So the idea is that what you're doing here is essentially you are shearing your paper. This transformation, because you are looking at another basis, right? So you might think of standard graph paper in R2, for instance, versus some shifted graph paper. So in that specific example that we just did, here's what the result looks like. So in the example that we just did, standard graph paper in R2 would look maybe, we'll say that it looks like this, right? So we've normalized it so that it looks like this. So we have vectors E1 and E2. Here's vectors B1 and B2 plotted on standard graph paper, right? So B1 was 1, 0. It's the same thing as E1. And B2 was 1, 2. Okay, there's our vector X, which is 1, 6, and standard. There it is graphed in standard graph paper. Okay, and then switching over to a viewpoint where we are now looking at B graph paper relative to this basis B, we have changed our outlook in such a way that now our axes are determined by B1 and B2. But they're not standard in the sense that relative to this standard graph configuration, they're skewed in some way, right? So B1 is still horizontal, right, in this way, but B2 is skewed. I'm drawing a skewed graph paper here now where my units are determined by, B1 and B2. So I have so many units up the B2 axis and so many units over the B1 axis. That's how I'm describing X here, right? So I am, minus 2 units over on the B1 axis, and I'm 3 units up the B2 axis. Okay, and this view is in some ways equivalent, right? Meaning that if it turns out that it is more convenient to do computations over here in this world, then the computations that I do they're somehow just as valid as doing computations over here. And so it's a matter of convenience for me if I want to work in another basis versus the standard basis. We'll talk more about that later when we talk about change of basis. Okay. So if we kept the grid moved to the points relative to one another instead, would this just be a well, this is a transformation anyway. What type of transformation it is depends. But this is a transformation anyway. In fact, it's a very nice transformation typically. Okay. And so let's do one more example before moving on to talk about the coordinate map specifically. So so our example is going to be so let say b1 be the vector 2, 1, and b2 be the vector -1, 1. This still forms a basis for R2. And let x be the vector 4, 5. Okay. And let script b, of course, be the set of the two vectors b1, b2. Okay, so find, so this is a basis for R2. I don't need to say anything more about that. So find the coordinate vector. So before we were given the coordinate vector and asked to find the vector. Now we're given the vector and asked to find the coordinate vector. So find the coordinate vector x sub b of x relative to b. Okay. All right. So how would we do this? Right. So the idea is that I'm looking for C1 and C2 such that x is equal to C1 B1 plus C2 B2. If I can find that, then I have directly that the b coordinate of x is just C1 C2. And that's the definition. Okay, but let's actually write out what this is. What is this? This is the vector 4, 5, and on the right, this is C1 times B1, so that's 2, 1, plus C2 times B2, which is -1, 1. Okay. So I can rewrite this as a matrix equation. Let's write it in the usual form where the matrix is on the left here. So this is 2 -1, 1, 1 times a vector C1, C2, which is exactly my coordinate vector, right, that I'm looking for, and that's equal to 4, 5. Right? Now this is going to tell me a lot here. So pay attention to the thing that I've written here, right? This is x sub b, right? And this is x, and this matrix, what is that? Well, it's a matrix that has b1 and b2 as its columns. Okay, but it's going to have a special name. Okay, this matrix is going to have a special name. It's going to be called a change of coordinates matrix. Okay. All right, so this is going to be my change of coordinates matrix. All right, so we'll write that out again here in a second. Okay, and so what is it that is going on here? Well, how do I solve this? I solve this by doing whatever thing you want to do here. This is just a 2x2. We could even find its inverse if it existed, right? But once you solve this equation, you find that C sub 1 is equal to 3 and C sub 2 is equal to 2. And so what this tells me is that the b coordinates for x are 3, 2. Right? So whether you found the inverse of that thing or you actually, solved it as a matrix equation by row reducing it, or you just did it by inspection, whichever way you did it, you solve it and you get these entries for x. Now, rewriting this line here is key. And what is that line saying? So define define P subscript B to be the matrix that has the basis vectors in B as its columns. This is my change of coordinates matrix. Okay. Then what this means is that X, the vector, is the change of coordinates matrix, right, from B to the standard basis times X relative to B. This is the important thing. So I'll write this again at the beginning of class next time. This tells me that this matrix, when I multiply, right, on the left by this matrix, when I have the coordinate vector here on the right, when I multiply on the left by the change of coordinates matrix, it changes my coordinates, my B coordinates, to standard coordinates. Okay. So my standard coordinates get changed to, or sorry, my B coordinates get changed to standard coordinates by multiplying by this change of coordinates matrix. Okay, so that's the key thing. So like I said, I'll do this at the beginning of class next time, and then we will finish coordinates and we will finish our discussion of dimension next time or on Wednesday, and you will have seen everything you need to know for the exam by the end of class. Wednesday, maybe I need to tidy up a little bit on Friday, but it will be almost nothing. So you'll have seen everything you need to know for the exam by the end of class on Wednesday. Okay. And so, and yes, this is just a fancy way of writing this. It's in a new setting, right? You're using a new setting here because the weights are the things you're solving for. Anyway, okay. So I have office hours coming up, so I'll send the link for those in a second, and I will see you all soon.